Hello, let's start. Who are these people? Why do I play this song? Do the reading? No, that's Kim Deal. Kim Deal, the bassist, who was in the Pixies and in the Breeders. The two. This is a very famous song of the Breeders. Cannibal. Okay. More fun facts about the textbook and music. And we're continuing our people. We're continuing our first order logic introduction. So it's part two of first order logic. I want to start with doing going over a very hard exercise that was in the homework. So that was question 16 in the formalizations of like the last exercise. Exercise 16 was a difficult symbolization exercise. So I want to, and I hope most of you are. It's kind of fresh in your mind because um, you just submitted it. So the question said, if there is an animal that is larger than any dog, then that animal does not like samurai movies. Okay, so it looks like, um, it looks like that this is an existential statement. It's very confusing. It looks like I'm saying something about a particular animal. So many of us, I've noticed in the tutorial and in the homework, we try to start out with the existential quantifier. But if you check the solution book, you see that it's actually a universal quantifier. Okay? So how is that so? The way the book wants you to read the sentence or to rephrase it as something like this. For any animal you will pick in the domain, if the animal you pick is larger than any dog, then that animal does not like samurai movies. Okay? So again, let's look at it together. If there's an animal that is larger than any dog, then that animal does not like samurai movies. We're saying go to the zoo, pick any animal that is larger than any dog. And if that animal is larger than any dog, then I'm saying that that animal does not like samurai movies. So you have an elephant, you have a giraffe. Both of these are larger than any dog. This sentence says, no matter if you pick the elephant or the giraffe or any other animal that is larger than any dog, those animals will not like the samurai. Okay? This is a bit confusing. Okay, so what do we say here? We say pick any animal you want, and then I'm specifying. This says this animal is larger than any dog. This is the antecedent. How do I know that? I can say whatever dog I pick, the animal I picked is larger than the dog. If this is the case, then that animal does not like sound. So this is why it's formulated with a universal quantifier. Okay. This is difficult. Okay, we'll go back to easier formalizations now in the lecture. Okay, but I want to flag that because I did not cover it in the tutorial and it was part of the homework. Questions about this? Yeah.
In this formula, the y and sy, it does not fall under the quantity.
Why? Yeah. Sure.
Okay.
That was a mistake. Any animal you pick, that animal will not like sound, right? So it's that x. Okay. Questions? Another way to think about if for all x this universal quantifier, you can think about the domain as like a big bowl with a lot of objects inside. The universal quantifier says whatever I pick in the bowl, in my domain, randomly, arbitrarily, that thing has to satisfy a certain condition. The existential says there is one particular thing I can take out, not everything that has a certain condition. But the universal says, shuffle, 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 whatever I pick, that will satisfy a certain condition. Okay? I go to the zoo, whatever animal I pick, I went to the zoo yesterday. Whatever animal you pick, there are 2 baby elephants, both of them are larger than a dog. I pick them, they are larger than a dog, then they should not like samurai movies. Okay? Yeah? Yeah.
So the first universal quantifier stands for type animal big. Then the next one is that animal. If you
Do you see the formula here? So whatever animal I pick, then I want to say if it's larger than any dog. But now I'm saying something about all dogs. So I need another quantifier to capture this, like saying something about all dogs. So I'm saying if the other thing is a dog and the animal I picked is larger than any dog I picked, then that animal does not like samurai. Okay, that's a tricky one. We're good? Let's go back to easier stuff. So today we start with a short recap on things I covered last time about empty predicates and multiple quantifiers and relational predicates. So this is a bit of a recap of last time. And then we're going to talk about identities. Okay? So we split up the chapter about first order logic in the book. The first chapter, which split it into 2 parts. And now we're doing the second part. Okay, questions? Okay. So we said that names must pick exactly one thing in the domain if we have a name, but predicates can fail to apply to anything. The predicate can be empty. And the example here is in the domain of people, there are no Pokemons. Okay, so the predicate P is a Pokemon is going to be an empty predicate. It doesn't apply to any person, to any people. Is cute does apply to people, so is cute is not an empty predicate here, right? All Pokemon are cute. This becomes for all X. If X is a Pokemon, then X is cute. Some Pokemon are cute. What will be the main quantifier here? Existential, right? So there is something such that it is a Pokemon and it is cute. So do you remember which one of these is true if there are no Pokemons in the domain? Yes?
Number 5, all Pokemon are cute.
Right, that's going to be true. Why is that? Because basically the antecedent is always false, right? There's nothing that satisfies the antecedent. So like in true functional logic, if the antecedent of a conditional is false, then the entire conditional is going to be true. We get this strange reaction, like consequence that sentences like these, all Pokemons are cute, we are taken to be true in first order logic because they don't apply to anything and they involve a conditional. Okay, so we call it, in such a situation, we call it a vacuously true sentence. Vacuously in the sense that the predicate here is empty, then if the predicate is empty and we have a conditional, that this is going to be always true. Because the antecedent is always false. Okay? Questions about this? Can you think of another example of a sentence like all F's are G, in which is going to be true by F being valuously true? What predicate doesn't apply on anything? Let's say all people. Predicate that doesn't apply to any person. Yes.
For all dogs, if they're dogs, then they're G's.
Okay, so you're saying the predicate, like you're thinking of the domain of people, and then you say no person is a dog, therefore that's going to be a domain, an empty domain. Okay. 10 meter tall, that's something that's a predicate. It doesn't apply to any human, therefore it's going to be empty predicate when the domain is all humans. Okay. Some predicates just don't apply to anything. Okay. Multiple quantifiers is the name when we kind of stack more, we have more than one quantifier in a particular sentence, and they interact in like kind of funky ways. Okay. So first, again, a recap from last time. We have one place predicates. So something like is a footballer. There is only one place here. Michael is a footballer here. Okay. Two place predicates ascribe relations between two things. So you have, this is a relation because it's a two-place relation because it has place for two names or variables. Okay. Michael loves Michael. That's an example. Okay. Is adjunct to, or like is close to, that's going to be a relation, right? You can also have 3 and 4 and 5 predicate relations. This is just like, you need to count how many empty spaces you have here. So X is between Y and Z. That can be a predicate with 3 places. Yeah. Most predicates we care about are have 1 place or 2 places. Okay. But in principle, there's no upper limit to the number of places a predicate can take. So you can have a predicate with 4 places. It starts to become like hard to think of it, but it's like it's possible. Questions? Yeah.
What is the last sentence? What does that mean?
And addicy of the predicate, like that's it's a fancy way to say, and if it's a 2-place predicate, sometimes you will see the expression dyadic relation or dyadic predicate. So die from 2 in Greek or Latin, and then you can combine it to say like, instead of saying 2-place, you can give it like a fancy Latin, but don't worry about it. Also, the 1-place predicate are also called sometimes unary predicates, from like the word one. Okay, unit. But these terms are, it's kind of like just if you see them that it will make sense to you. But it's more important to understand the idea behind it. Yeah? Okay, so the spaces, we've emphasized, it's important what you put in each space. Okay? This is something we also practice in this exercise, in last week's exercise. But we want to make sure you understand this. So Finn loves Princess Bubblegum. What will be here? F, right? And here B. So LFB. Finn loves Finn. How will you do that? LFF. Finn loves Princess Bubblegum, but Bubblegum doesn't love Finn. What is the main operator here? Main connective? Conjunction, right? So you have a conjunction. And then you can say something like this, expressing that, the one can be true and the other one might be false at the same time. Okay. And English can be confusing. You can say things like Princess Bubblegum is loved by Finn. Also, this is not special for English, other languages also have it, but this has the same meaning as the first sentence, right? Just like it's still LFB, okay? Can be confusing in the homework we had like X larger than Y, so we kind of like, okay, have to sometimes stop and say, okay, X refers to this, and then we're saying that the elephant is larger than the dog, so if X is going to be the elephant, and the order is going to be X. I actually made a mistake. This mistake when I wrote it on the board for the first time. It can be confusing, but we're saying any animal that is larger than a dog, so this is the dog, X is larger than 1. Same again. If I will do this, that would be a mistake. Okay? This says that any dog is larger than that animal. Completely different meaning. Doesn't apply to baby elephants. Okay? So it's important to keep the right structure, right ordering. Questions about the position of the predicates? Okay. The multiple predicate case, okay? What we said, there's a difference between saying for all X there is a Y, and there is a Y such as for all X. Okay? These are two different, they have a completely different logical structure. Okay? The example that is being used to describe it, how would you formalize everybody loves somebody? Okay, I think the natural way to understand the sentence is to say, for every person you pick X, there is some other person Y that X loves. Okay, but the Y can be different for every X you pick. Right? This can be contrasted with a sentence like there is some particular person X whom every person loves. Okay, so you pick one person and everything applies to that. Okay? So in a love triangle, where every person you pick among the three people loves someone else in that triangle, the structure for all X there is a Y is true. Ron loves Hermione, but not Harry. Harry loves Ron, but not Hermione. Hermione loves Harry, but not Ron. So there is a love triangle. Every person you pick, A, B, or C, whatever I pick, whatever I shuffle and pick, there will be a different person that person loves. Okay? And that's different than saying there is some person that everyone loves. Okay, that will look like this. There's maybe person A, such that A loves A, and B loves A, and C loves A. Right? These are different situations. Okay? We called the mistake here, if you mistake these two, do you remember how we called it? What happens if you, how do we call the situation where people mistake these two logical structures?
Quantifier shift fallacy.
Right, that's a quantifier shift fallacy. It's actually happening a lot. Okay, people confuse it all the time. This is why we study logic, to kind of clarify a few things. Okay, questions? Okay. How would you write Michael is a fan of a dancer, given this symbolization key? Okay, so we need to use this relation, 1 is a fan of 2. Okay. Do I have the name of the dancer? No, right? Because I don't have the name of the dancer, it has to have involved what? A variable that is bounded to. The variable cannot stand alone, right? The variable always comes with a quantifier, right? So what the quantifier will be in this existential, right? I'm saying there's an X such that X is a dancer, and Michael is a fan of X. Okay? There is an X, yeah.
But why don't you say, like, for example, F and then you cannot say universal X in that?
So this says that you can say for all X, if X is a dancer, there's this sentence, okay?
Yeah.
This says that everyone in the domain is a dancer,
And
and Michael is a fan of them.
but you can also not say it in the predicate. You cannot have a large A.
Large A says, so this will say for all X, large A, X says that everyone is a dancer.
I will draw it in the break. I can
Okay.
explain it now.
Yeah.
You can also quantify between the conditional set of conjunctions.
There is no like, this is a well-formed sentence. It's just like it doesn't capture nothing close to what we're saying here. This is okay sentence. It just says everyone is both a dancer and Michael is a fan of dance. This is not what we mean by Michael is a fan of dance.
Why can't you change that conjunction into a conditional, for example?
People, I hear a lot of chatting. If you have questions, read it. The sentence for all X. Let's look at this sentence and try to understand what it means. This is a different sentence saying any person you pick, if that person is a dancer, then Michael is a fan of them. So this says Michael is a fan of all dancers. This in here we're just saying there's at least one dancer.
Yeah, but I was wondering if you put existential before it, before the conditional.
So here I put it before.
No, I don't. I mean, you put a universal, but I meant existential X. Why can't you change that conjunction into a conditional?
You're saying change this to existential.
Yeah.
This says something weaker, basically. And this might be true if there are no dancers, again, because of the empty predicate. And when I'm saying Michael is a fan of a dancer, I'm meaning that there is someone who is a dancer and Michael. So we want to kind of like commit ourselves to the existence of at least one dancer in this sentence. Okay, other questions about this? Someone is a fan of a dancer. Okay, so now we kind of like, the idea here is that we realize being a fan of a dancer requires a quantifier, and then we're adding another quantifier on top of it. So since like someone is a fan of a dancer, that will need to involve two quantifiers. Okay, there is an X such that X is a dancer, and there is someone else, Y, such that Y is a fan of X. So there is someone, Y, who is a fan of a dancer. Okay, the way you think about it is like, well, there are no names here. Someone is a fan of a dancer, but I'm talking about two people, right? At least two people, the dancer and the fan of the dancer. So I need two entities to talk about. I don't have any names. Two entities, I have to have two quantifiers here, okay? An X and a Y. All of Michael's friends are fans of dancers, okay? That's, how do we think about that? So this is like kind of similar to what we do here. First, let's try to rephrase this. I'm saying everyone that has the property of being a friend of Michael also has the property of being a fan of a dancer. Okay, so I'm breaking it up. What is going to be the main quantifier in this sentence? conditional, but what I'm saying something about everyone, right? So it has to be a universal quantifier together with a conditional. You're right, yeah. For any person I pick, if that person is a friend of Michael, then that person is a fan of a dancer. Okay, now this is kind of like still in bastardized English. We need to replace this with first order logic, but X is a fan of a dancer is already something that we've seen here. So we need to add another quantifier saying there is a dancer and such that X is a friend of that dancer. Okay, so this is how we get multiple quantifiers working together in such a complicated sentence. Okay, so for all X I pick, if that X has the property of being a friend of Michael, then there's another thing, another person, that person is a dancer, and the person who is the friend of Michael is a fan of the dancer. Okay, this is why first order logic, remember I told you last week that first order logic is very, very expressive, it can do a lot of things. We start to notice, there are all these like type of relations that we can capture with first order logic. Yeah? Yeah.
Does this last sentence include Michael? Because it can use on that.
Right. This is we're not excluding the possibility of picking Michael here, or actually picking Michael. You're right. We haven't said that Michael is different than X or Y. Okay, we'll see today how can we say it. Okay. Questions? People? Questions? Okay. When you see these more complicated sentences, the way I want you to do it is to start. If it's hard, try to rephrase it as a different English sentence or a Dutch sentence, and then work slowly to see what you do. If you want to, and another way you can do it also backwards, you can get some answer, okay, and instead of like, you can see in the textbook, in the solution book, I got a different answer, what's going on? The answer that you have, try to now read it in English, okay? You get some sentence first or logic, and then ask yourself, how would I read it in English? Try to write it down in English. With the expression like, for every person I pick, if that person is a friend of Michael, then there's another person, right? It's kind of cumbersome, but then ask yourself, is the sentence that I created in English using my first order logic formula, does it have the same meaning as the sentence I started? Okay? Questions? Is this hard, easy? Hard. I guess it's hard because I'm kind of like telling you how to do it, but it's not obvious how to do it yourself, right? So it requires a bit of exercise. Multiple quantifiers are the reason why first order logic is complicated, basically. Okay, you can start saying for all X there is a Y, such as for all Z there's a T. You can create a massively complicated sentence. Okay? But remember, if you're stuck, take the sentence, try to say it in as close as possible to like first order logic, but in English or Dutch. Say like, for all X, if X is this, then X is that. Okay, you get something like this. That's a lot. That's already like a lot of work. Okay? Okay. Identity. Identity is an addition to first order logic. Identity allows us to do extra things about, it allows us to say more things about our objects. Identity is this sign, okay? You know this sign from where? Math, okay?
Wow.
Math. It means the same thing in logic, but we read it a bit differently, okay? It's important to realize it's not like we're not solving equations here. It's the same symbol, but it's treated a bit differently. This sign always means, it's always a two-place predicate that says, this thing is identical to that thing, right? It's always have the same interpretation. So you don't have, in the symbolization key, for example, you don't have to specify what the sign means. Okay? Note it does not mean that X is indistinguishable from Y, or that we have X and Y and they have the same kind of like properties. No, it does not mean that. When I'm saying A is equal to B, or A is identical to B, what I'm saying is there's only one thing, and I have two names for that thing. There's only one thing, and A is the name for that thing, and B is also the name for that thing. Okay, so identity says we're only dealing with one particular thing. Okay? It does mean that the objects involved are actually just the same object. Okay? There are no two objects. You cannot say this distinct object is identical to that distinct object, because no, there you actually say there's only one object.
So it's like a bachelor is a man.
No, it's not.
It's not, okay.
Okay, good. A bachelor, this is a general term. A man is a general term.
Okay.
Identity is a very good point. It's not written here. Identity only works on singular term, about objects. It does not work for predicate. We don't use identity to say this predicate is the same as that predicate. First of all. We only mean, when we use identity, we only talk about the object, the singular terms. Okay? Superman is Clark Kent. What does it mean? I can say M stands for the name for Superman, and C is the name for Clark Kent. But I'm not saying there are two people, Superman and Clark Kent, and they are equal in their, I don't know, income or something. No. I'm saying, no, it's actually just one person, and we have two names for it. Okay? Yes? There's this logic joke, not very funny, but it makes the point, where a logic student is being asked, oh, you're smart, what is this? Let's say, what is this identical to? Okay? 106 to the 5th plus 100 to the 6th times 7. Oh no, this looks hard, right?
Write that in the same thing.
Right. This is logic, right? Logic is easy. Well, that thing is identical to that thing. I know that, right? So I'm done. This thing and that thing are the same thing. So I can use identity on both. Okay? Won't work in your high school math, but it works in your logic class. Okay? Why do we care about identity? Why do we add identity? Anyone figure that out from the book? What does it help us do? If you read the textbook, I know it's already week 4, so yeah.
Maybe like clarify that those two are the same thing.
Right. Sometimes you want to clarify when you have multiple quantifiers, you want to say, wait, the x I picked and the y I picked I'm specifying particularly they're different things. Because otherwise, you could just pick the same thing, right? Remember the shuffling? I can shuffle the same object as well. Okay? That's the general power. Like you can say, this thing is distinct from that, and blah, 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 blah. Okay? So some Christmas Carol and by John Dickens. This is like the example. Okay, so Scrooge hates everyone. How would you write it down? The most direct way to write it down in logic. Say it with the quantifiers. Universal, yeah, universal, and then what? Age.
HCX.
Right. For all x, Scrooge hates x. What follows from this? Does Scrooge love himself? No, right? Because Scrooge also hates himself. Because I can take the X here to be Scrooge, right? So this says, without any additions, that Scrooge hates everyone, including himself. But what if I want to say Scrooge hates everyone other than Scrooge, or Scrooge hates everyone except for himself? So how would you say that? Now I need to use identity symbol, right?
I have a question about the first.
Yeah.
Why do you have to put in the universal? Because when you leave it out, it says the same thing, right?
So if I leave it out, it says H C X, right?
Yeah.
But what is X? You're not telling me what is X. What does X refer to? X alone, we will get to it later in this lecture. X alone, what is not connected to a quantifier, doesn't mean anything, right? It's a placeholder, but you didn't tell me how to, what to do with it. So basically, when you see an X that is not connected to any, you see a variable that is not connected to any quantifier, basically, you don't know how to read it, right? It's kind of like a placeholder. It's like in English when you use he or she or they and you don't know what the he or she or they refers to. It's kind of like you cannot interpret this sentence. Okay? Yeah.
I wanted to ask if you wanted to solve this. Did you need a negation?
You need a negation, right? Because what does it mean to negate an identity claim? Saying that the two things
Are not the same. It would mean that Scrooge could not be X.
right. You can say, you can express the fact that Scrooge is not X by negating the identity. And you can say, now Scrooge is not X, right? But X, again, it's a placeholder, we didn't specify what it means. What quantifier can be connected to? What do you think? We're saying something about Scrooge hate everyone.
And every X.
Right, for all X. Now saying, if X is not Scrooge, then something follows, right? For all X, if I negate the claim that they are identical to Scrooge, then that Scrooge hates that X, okay? So one way to negate an identity is to do like this, negation and identity. But if I also just like to, do this, it has the same meaning as far as we're concerned. Okay? This says A is not identical to B, or you can write it down as like this. Or the book doesn't even use brackets. You can also say they all mean the same. Yeah.
What would you do if someone named like Scrooge and somebody else? So you would negate X and then equals C. Like a combination between names that.
You can use the identity for names and for variables. So you can say Scrooge hates Bob. Let's say I can say Scrooge hates Bob, and I can add the fact that Scrooge and Bob are not the same person. So I can say something like this. Okay, do you see that?
But in this last sentence, if you put like both, so everyone who is not Scrooge or Bob is hated by Scrooge or Bob and Bob, maybe. How would you like write it down in the further down?
Yeah.
So it's like this negation X and then is equal to C. How would you put like the C then, like B or Bob? Is it possible?
It's not possible because we only have one name. In all these senses, we only have Scrooge as a name to play with.
So no, but in the case that that's your names.
So let's see. We have this example. So now we have Bob and Tiny Team. Okay. Who read A Christmas Carol? Well, you should be able to interpret this. No one besides Scrooge hates Bob. There's a typo here. Cartwright. Okay. Okay? No one besides Scrooge hates Bob. So now we're saying it's not true that everyone hates Bob. But there's an exception, right? There is no person, okay? It's not true that there is a person such that that person is different than Scrooge, and that person hates Bob. Okay, yeah.
But couldn't you make this sentence easier than just saying Scrooge hates Bob? I mean, that's what it says already.
No, that's not. So this says something stronger. It says that Tiny Tim doesn't hate Bob as well. Okay, so any X that is not Scrooge is not going to hate Scrooge. Another way to write it down. Remember, this is just like from last time. So when you have no F's or G's, there are two ways to write it down. So I can say for all X, if X is not Scrooge, then X does not hate Bob. Okay, remember from last time we said that these two forms are equivalent. For all X I pick, if that X is not Scrooge, then that X does not hate Bob. Okay, so this applies to Bob as well, to like Tiny Tim or any other name.
So you could write that down as an answer to this question.
Yeah, because in general, no F's or G's, which is kind of the structure here. No one who is not Scrooge has a certain property. There are two ways to write it down. Yeah.
I have a question. If we on the test that maybe everybody hates Scrooge, do we assume he hates himself, or do we assume he doesn't?
You never, no, this is logic. You kind of take the sentence and you move it into the logic. If there is no indication that we're ruling out it's called the reflexive case because the thing applies to itself, then you don't have to specify it. So in general, the universal quantifier applies to everything, and if in English you see everyone, it means everyone.
Okay. Yeah. Okay. And my second question was, the equal sign, the thing, we can use that,
I use it, so I will probably use it on the board.
but we cannot use it in the test.
If you use it in the test, we just let's agree that we all mean this. Just an abbreviation of negation. Because identity is a special two-place predicate, you can also have a special negation sign. But remember, this just means this. It's not true that A equals X. Okay? Only Scrooge hates Tiny Tim. Okay, how do we say it? Here we say, again, it's confusing because we're actually saying something about everyone. We're saying every people are such that if the person I picked hates Tiny Tim, then guess what? That's Scrooge. By the end of the story, this is even that is not. Scrooge learns his lesson. But in the beginning, everyone, if they hate Tiny Tim, then it must be Scrooge that hates Tiny Tim. Okay? It's very weird because we're saying something about everyone, and then we're actually saying, no, we're actually mean it for one particular object, or name. Right? Yeah? Okay. Yeah.
The last slide, yeah. Don't they imply the same thing, that it's just Scrooge that hates someone? So only Scrooge hates Tiny Tim, couldn't that also be no one besides Scrooge hates Tiny Tim? Yeah, this is reply.
No, I think, yeah, you're right. They mean the same thing. Yeah. If the person hates Tiny Tim, then that person is Scrooge.
So you could also answer the second sentence with FOL.
Yeah. And by the way, I wrote this down, okay? Which is it's a different way of saying it. But it's actually identical, it's equivalent to this one because of the TFL equivalence that you should know for life and for the midterm. Check for yourself that this sentence is the same, is logically equivalent or tautologically equivalent to that sentence. Okay, that's actually important to know for life. You can get ahead in life by noting that if A then B means the same thing as if not B, then not A. Okay, so this is what happens here. I said if they are not the same, then they don't hate, and if here you said if they hate, then they're the same.
So both sentences say
Yeah,
something similar or something what is wrong.
right. Remember that many times when you have like no F's or G's, things like that, when you negate a quantifier, there's a way of doing it with the existential and a way to do it with the universal. Okay. Okay, let's take a 15-minute break and let's come back at 11:45.
Deze les stopt. De eerste les
1, 2, 3. Let's come back. Okay, let's continue. There are many more fun things to do with the identity. We just started with the identity. There is more. The identity. Okay, so we need to cover it. There is at least one beer. People, how would you write down there is at least one beer? Do you need identity for that? If you have B for is a beer, so how would you write it down?
Existential X and then EX.
Right. You just said there is something which is a beer. So there is at least one thing. Remember, the existential doesn't care about counting. It just says, basically, the existential always says there is at least one. Okay? But what if we do care about counting? Okay, what do we want to say? There are at least 2 beers. Okay, if I say there's an X, there's a Y, BX and BY, that looks in the right direction, but it's red. Red means wrong, right? Why? What's wrong here? Yeah.
It is possible that it's the same beer.
Right. The fact that you use X and Y, again, does not rule out that you actually pick the same thing from your bucket. You have to specify that the X and the Y are different. Okay, so you can specify it by, yeah, this is what I said. You can just add the specification, and by the way, X is not the same as Y. So now I know, because I'm saying X is not the same as Y, proof logic, I basically said there are 2 things. Okay? Remember, identity means if you say X is identical to Y, you're basically saying there is one thing, and I can refer to it as X, and I can refer to it as Y. But it's only one thing, and if you negate it, you're saying it's not one thing. There are at least 3 beers. Okay, you get the idea. Now I can say there is an X, there's a Y, there's a Z. All of them are beers, and X is not identical to Y, X is not identical to Z, Y is not identical to Z. Okay? If the bucket only has 2 things, the sentence is going to be false. Yeah.
This doesn't really seem like a foolproof method, for example, to 1 million beer.
A very long sentence. At least 1 million beers. A very long sentence.
That you will be infinitely writing.
No, it's a finite sentence still. It's a very long sentence. I like your thinking because I like infinity. But 1 million is still a very small number in the grand scheme of things.
Yeah,
And for billion.
you would write the first beer is not the same as
The second and the third. Yeah.
100,009 beer.
Right, so you can use, if you really want to, you can use a subscript to have for variables, and then you have as many as you want. Okay. So you can say, you can basically reach any number, any. Yeah, you know.
It's extremely efficient to yes. Isn't there an easier way to write this down, like a shorter way? Because this seems like very redundant.
It's not redundant. So like there is this is like the shortest way to do it basically. You have to specify there are 3 different things. So because 3 things, you have at least to have 3 variables, and then you have to specify for each one of them the difference. Okay, so what sometimes people do, like not in this class, but you can say, let's just say like 3x or something like this. This kind of specifies that you abbreviate this thing. But you still need to have 3 variables, x, y, and z. If you take any part of the sentence, it will mean something else.
I understand, but is he never going to on the point that we're going to Isn't something easier than this?
No, that is the easiest it can get. I won't ask you like in the exam, right, there are at least 99 beers on the wall or something.
Do you need to specify for each variable that they're not the same as every other one? So like here, there's 3, so you can say x is not y, x is not z, and then y is not z. But if there are 4, would you have to also?
Yeah, you have to like kind of like make sure that you negate all of them such that they're all the same.
So for each one, you have to do it for everyone?
The point is to realize, so the point here is to realize what first order logic can do. I'm not going to ask you to like write it down, but you now notice that you can do it in first order logic, even if it's kind of like long and ugly. Okay? Questions?
Yeah, I'm thinking about what you said that you have to specify that each one like, isn't the same as another one, because if I say that x and y are not the same, and I say,
That y and z are not the same.
yeah,
Is it possible that x and z are the same? Okay, that's logic. Okay, that's like identity has certain fun properties. Okay, if x is identical to y, then y is identical to x. So identity has this property of symmetry. It's called, and if y, like you can, the order doesn't matter for identity, so it's symmetric. Don't worry about this. We're not going to cover like all the properties of identity, but there are special properties for identity. Can something be not identical to itself? I had a friend who wrote a PhD thesis about it, but no, in general, no. Like everything is identical to itself, right? So you can, okay. This is always going to be true, right? For all x, x is identical. So the identity is special because it has all these properties, as opposed to hate or love, where like it matters. If you love yourself, you hate yourself. Right? Identity, you're always identical to itself. At least you know that in life. Okay. There is at most one beer. What am I saying there is at most one beer? I'm saying there might be 0 beers, there might be 1 beer, but for sure, there are no 2 beers, right? This is the idea of at most, as opposed to at least. At most, you're kind of like giving the upper limit. So if there are no beers, there's at most 1 beer, right? Okay? It's not the case that there are at least 2 beers. I negate the claim that there are at least 2 beers. So there's either 1, there's 0. So one way to do it is to negate the sentence, and there are at least 2 beers. You get what? Okay? I find it a bit confusing, so there's another way of saying it. This I find easier. If you pick out anything it's a beer, then pick out anything out and it's also a beer, then you must have picked the same thing. Okay, again with the idea of like the box. Whatever I pick, if I pick a beer and then I pick something distinct, then that thing and it's not going to be. Okay, so you can use the universal to say it as well. For all x, for all y, you're kind of saying, maybe they're different, maybe they're not. If x is a beer and y is a beer, then x and y are actually the same. Yep. Because, so you're asking about replacing here 2 existentials.
Yeah.
And then use an implication. I need to think about it about a counterexample. In general, the rule that we follow exist goes with a conjunction, and universal goes with a conditional. When we're trying to remember saying something general. Okay. The point here is that you say how, like, pick an arbitrary thing. When I describe a situation where I pick an arbitrary thing, then it's the universal quantifier. I'm saying, like, pick an arbitrary x, that x is a beer. Pick another x, another arbitrary thing, y, that y is also beer. If this is the case, then they're actually the same thing. But the structure of, like, if you pick a beer and you pick another beer, I'm saying in full generality, I'm not talking about particular objects. So this is why I'm the universal quantifier. Yeah.
Is the second bracket in the second sentence a typo?
Yes, it is. Why? Because it's impossible to have two open brackets in English, in Dutch, or in logic, and then only one. Yes.
I thought maybe you forgot one.
Maybe the sentence continues. Yeah.
Still satisfied with the answer. It's still a particular variable.
If you pick out anything, and it's a beer. So whatever you pick, if that thing is a beer. I'm saying something general, and then I'm specifying to it being a beer.
Okay, then the other way around as well. Why not give at least one beer? Why don't you use it for a universal quantifier there?
And the condition and the existing. Because then you say everything is a beer if you do it with a conjunction.
This is any arbitrary thing, it's a beer.
Okay, that's a good point. So at least says that it's more than zero. Okay, this is why you have to use an existential, because you're saying there are at least two beers, then you're ruling out that there are zero beers. So you have to use an existential and a conjunction, because then you cannot be in the situation where the sentence is vacuously true. Okay, now here, it's another way to understand the difference. This is also true if there are zero beers, because then the sentence is going to be vacuous. But this is only true for its most, because it's most, I'm saying there might be one beer, there might be zero beer, but there are no more. Okay. These two ones, yeah. I like to think about this one. If you kind of randomly pick one thing and it's a beer, and you randomly pick another thing, it's a beer, then they're the same. Yeah.
So the second option you could only use the most one beer or zero beers.
At most, one beer says you either have one beer or zero beers, but you don't have more than that. This is how I'm thinking about it most. And at least says, like at least two says there's two or three or four or five, right? Or blah, blah, blah. Now, there is at most one beer. I can also say there are at most two beers, and I follow kind of the same logic here. It's not the case there are three or more beers, so I'm negating the at least claim. That's long, okay, but it just follows the same idea. I'm negating the claim that there are at least two beers, okay? Sorry, at least three beers. So this was the sense there are at least three beers. I'm negating the claim that there are at least three beers, then it means that there are 0, 1, or 2 beers. Okay, it's confusing. Suddenly it will make sense why we care about at least and at most. Okay, so there are at most 2 beers. I'm basically negating the claim that there are at least 3. I'm saying it's not true that there are at least 3 beers. This can be done like this, or you can say it also in the general term. If you pick any object and it's a beer, and you pick any other object and it's a beer as well, if you pick any other third object and it's a beer, and then you will have picked at least one of them twice, okay? So in terms of structure, you say, if in your bucket you pick 3 things that are beers, then either X is going to be Y, or X is going to be Z, or Y is going to be Z. Okay? Yeah.
I still don't really get my universals being used there, unless it's not.
Is it clear for the first one?
No.
So the first one is should be clear. Okay. So there's a beer and there's a coffee. Remember my game of like picking something, picking something. So I'm doing it twice, but I'm kind of potentially putting it back. Okay? So I'm like, what? How can this be true? There's only one beer here, right? So there's at most one beer. I'm saying if I pick something, let's say I pick this, and then I pick again and I pick this, then this is the same thing. I cannot pick beer twice, so to speak, in this picture, because there is at most one. Basically, if I do this process and pick two things which are beer, I'm saying no, it weren't two things. It was actually one thing that I picked twice. If I pick two things that I thought like two beers, I'm saying no, they're actually the same.
But if you could you maybe show what would happen if you do switch them to extension?
So you're saying this claim?
What am I saying here?
Existential and conditional are very confusing. You're saying there is a thing such that there is another thing, such that if this thing is a beer and that thing is a beer, then they're the same thing.
So then
Here you don't say whatever I pick. Okay, here when you say the universal, you say whatever you pick. It's going to be it's going to hold. Here you say there are two things that I can pick, such that sorry, yeah. So here's an example actually. There are 4 beers in my bucket. Okay, and this says I can pick a particular thing, and I can pick another particular thing, such that they're both beer and they're the same. So I can pick this object twice, and this sentence will be true. But of course, this is not a situation where there's more than one beer, there are actually 4 beers. So there's more than one. Okay?
oh,
I'm saying I can pick one particular thing, so I can always pick this thing.
because you're not checking every
Right.
possible thing. So
Right. Here, when I say why is this false? Like this sentence is false in this bucket because I'm saying not only this thing I pick, whatever I pick, they have to be all. Okay.
Yeah, I see. Thank you.
Thanks. It's like, yeah, it's. This also answers kind of the same line when with your question of what does it mean to like do an existential and evolution. Okay, these are good points.
The last example is the bucket for beers.
Yeah.
How does that work with the universal quantifier?
Yeah, let's ask why this sentence is false here.
Yeah.
I can pick this to be x, and I can pick this to be y, and x and y are different. So I do have two things such that they're both beer and they're not the same. Okay, remember, the universal says whatever you pick it random. Like you can pick whatever you want. So I picked for x this one, and then it says you can pick whatever else you want. So I can pick this one. And then, but they're not the same. So the sentence becomes false. We'll see the connection to like truth and falsity more when we talk about interpretations. Okay? I haven't really told you about how to say at first a sentence is true or false at first or not. So it can be a bit confusing. But this is kind of like, I hope the picture kind of helps. Okay, exactly one beer. What am I saying, basically?
That is, the installed beer is
Right, I'm ruling out the case that there is 0 beers, so there's at least 1. And I'm ruling out the case that there are 2, so there is at most 1. So exactly just is the conjunction of at least and at most. This is why exactly in natural language is a very easy concept to understand. But in first order logic, you need to formalize at least and formalize at most. You conjoin them and you get the very natural term exactly. Okay? So it's basically a conjunction of the last 2 slides. There exists a beer, and for any, if I pick 2 things arbitrarily, and both of them are beer, then they're the same thing. Okay? Again, this is false here because I can pick this thing and that thing, and they are not the same. So it's not true here that there's exactly 1. In this bucket, it's true that there is just 1 beer, and I'm saying if I pick 2 things and they're both beer, then it has to be the same. So this sentence is true for this bucket. Okay? It helps me to think about domain as buckets, basically. Yeah? Or as a fridge if you talk about beers. Okay? You can also, this is where first order logic kind of I would not expect you to realize that just by what I taught you. Now there's an equivalent way of saying that, which is kind of shorter. I'm saying there is something such that that thing is a beer, and for any other thing I pick, if the other thing is a beer as well, then actually they're the same. So I'm basically saying the same things here, but I'm doing it with I'm pick 1 quantifier to do it. Okay? But this is clear why this says there's exactly 1 beer, right? The conjunction here is inside the existential quantifier, but they mean the same thing. Now we can say there are exactly 2, there are exactly 3, there are exactly 1,000,000 things. How? We combine the at least 1,000,000 with the at most 1,000,000, and we get exactly 1,000,000. Very long point. Let's look at the 2 case. Exactly 2 beers. There's at least 2 beers and at most 2 beers. Okay? So here I'm saying there are at least 2. Here I'm saying there are at most 2. Conjunction, you get that there are exactly 2. Okay? Basically, in first order logic, we can count things. Extremely impressive. You're like, wow, I can also count things. But it's impressive that I can do it from only talking about exist something and for all things. I can get these notions of 2, 3, 4. Okay? This says there are at least 2 different beers, and every other beer is one of the 2, right? There are 2 different beers, and whatever other beer you pick, it's actually one of the 2. So again, you can kind of compress that. I would not expect you to realize that, but again, you can say there are 2 things. They are both beers. They are different, so there are at least 2. And for any other thing you pick, if it's a beer, then it's either one of the 2. Okay? First order logic can count. Very impressive. Or if you want to sound philosophical, you can say you reduce the notion of counting to only quantifiers. So counting is not some basic notion in our head. It's actually something we can reduce or analyze to something else. Here?
Yeah.
Because I already said that x is not y, so that we right? So x is not y, I said it up to here, and then for any other thing, it's going to be x or y. But you're right, here it's different because here the scope of the existential only applies this part. Here the scope of the existential actually goes all the way to the end. Okay. And I will get, like, there's slides for that, but just note that this x, I stopped talking about it here. Every other x that comes from this direction is actually connected to this quantifier. However, this x and y, they actually, when you talk about this x, you go all the way. Okay. Questions in the back? Okay. Okay, so now you can write, there's exactly 2 things, exactly 3 things, exactly 4 things, and so on. Very exciting for for the people who, basically, so to give you a bit of history, people thought about the idea of like reducing all knowledge of, let's say, mathematics to logic. Actually, everything you learned in your mathematics class is basically logic. How do you show that? What the first thing you need to show is that counting, something you learned in first grade, is actually logic. You don't start with this in your first grade because that's hard. But philosophers have shown that actually it just boils down to logic. There's this famous, it's almost a meme now that like Russell and Whitehead, they wrote like a huge book about logic, and then like in page 400 they proved that 1 + 1 = 2, right? So, okay, these are the people who came up with, okay, you need to know what 1 is, right? So they're exactly 1. These are the people who gave you 1 + 1 = 2. So mathematics, all your knowledge in mathematics can be reduced to knowledge of logic. And if I can go beyond the realm of this class, for Kant, for Immanuel Kant, for example, that would be like devastating conclusion, okay? Very important in the history of philosophy, but this is not what I'm here to teach you. Okay? People? For summary, when I say there are at least n apples, I'm saying there are n apples or maybe even more. So the number of apples is greater or equal to n. When I say there are at most n apples, I'm saying they're either 0 or 1 or 2, but no more than that. And then I can say exactly n apples by conjunction. So there are exactly n apples, and there are at most n apples. N is exactly the number of n. Okay? We've seen how to formalize at least. We've seen how to formalize at most. So we have counting in logic. First order logic. Two-functional logic could not even imagine that. Yeah. Okay. Definite descriptions. This is another thing you can do in logic. Okay, let's see if we'll manage to cover it. Remember, there are 2 types of singular terms. Singular term is an expression in language that picks out a particular thing. A dog is not a singular term. You pick up a unique, specific. The 2 ways of picking out things in language is either by name, so like Michael Cohen, that's my name, picks up me, or I can think about a good description that only applies to me. So if I'm saying the 33-year-old father teaching logic in Tilburg University Philosophy Department, oops, I managed to, with English, point at this person here, right? Because I'm the only person, this description definitely applies to at the moment. So it's called a definite description. In a way, it defines this object. Okay? There are also indefinite description, things like a 33-year-old father or a philosopher. These expressions apply to many, many things, right? They don't apply to a particular thing. There are many, many 33-year-old fathers, but there is only one who currently teaches. That's the difference between definite description and indefinite description. In English, of course, you use the to describe definite description. In Dutch, you have two options. You can do de or het. Three, okay, whatever. Too much for me. Okay, how do we symbolize definite descriptions in first order logic? Do we have any symbols that describe definite descriptions? We have names, we have equal sign, we have variable. There's nothing that says the x such that blah, blah, blah. Okay? So people go, this is where first order logic doesn't manage to capture everything. And the same guy came up, Russell, and he showed we can symbolize definite description in first order logic. Okay, so this is the level, right? We give you in a homework assignment, symbolize this language, English sentence to first order logic. Russell came up with a sentence that he was like so impressive, this formalization, that he actually published it, and it became very famous. Okay, so we don't expect you, not everything we expect you to formalize, but Russell here came up with a nice idea to do it. So how do I capture VF, where F is some description? I'm saying there's at least one F, and there's at most one F. Okay, so there's exactly one F. Right? Remember, there's at least one person who is a 33-year-old father teaching logic. There's at most one person who is a 33-year-old father teaching logic, so there's exactly one. Right? So I managed to say the F is something with the exactly one tool that we already saw. And how do I say the F is a G? The 33-year-old father who teaches logic at the moment is very happy today. The G is very happy. I say there's at least one F, there's at most one F, and every F is a G. Okay? So I managed to break this sentence into three components. We saw how to do this, we saw how to do this, and this is just for all F. If F is an X is an F, then F is a G. Okay, so let's look at an example. There's at least one F. Okay, we know how to write it. There exists an X, Fx. There's at most one. For any other Y, which is an F, it's actually the same, and it's a G. Okay, so this is the sentence, the F is a G. There's an X, X is an F. For all Y, other Y, they're actually the same one, and the F is a G. Okay? So Russell showed in a paper called On Denoting that first order logic can also manage to capture definite descriptions. And there's a long history in philosophy of language of why definite descriptions are important to analyze, which we'll not go into. But yeah.
What does F mean? Could F mean in this case?
The F is always like a definite description. So think about a description that is so good that it captures a particular, only one person. And I can say the current teacher in this class, this is also a definite description because it only applies. Yeah.
Why can't you just use an equal sign?
Good, because equal sign always applies between names and like between objects, right? But F is not an object. F is a predicate. I cannot say in first order logic F equals to B, right? This may be the idea that you have. But B is equivalent to this property of being F. But this is not a way to talk in first order logic because this is a predicate on the one hand, and this is an object. Identity only works when you have two objects.
But in this case, it's two predicates actually, because it's supposed to be G,
So df is a G, so df is the definite description, and then you give it some property. The current teacher in this room, that's the definite description. He's very happy, that's the extra description that you give to him. Okay, so how would you write the wrestler? Talking about Dwayne "The Rock" Johnson. there is someone who is a wrestler, and for anyone else, if they are a wrestler, they are actually the same person. Okay? Now I'm saying that this description, the wrestler, only applies to exactly one thing. So it's a definite description. Note that this is not a sentence in English, right? It's only like a part of a sentence. So now I can say Dwayne is the wrestler. Yeah, question about the first one?
Doesn't the wrestler then imply that there's no other wrestlers in the world?
Right, there's exactly one. This is like a definite descriptions always do that. They always imply that you picked one thing. Okay. In a way, this is why we care about, I cannot stop myself from talking about philosophy of language here. Why is philosophy of language interesting? The question, one of the biggest questions in philosophy of language is how words in English capture things in reality, particular things. How is that connection possible? Definite descriptions are the first way to look about it. Okay, so now I'm equating a name with a description. How would I do that? I start with my description and then I add, and by the way, that X, which is the wrestler and the only wrestler, is identical to Dwayne. So I have a sentence, Dwayne is the wrestler. So you say you replace everything with a D, right?
Yeah.
But you want to say that there is like no more than, so you're saying Dwayne is a wrestler, there might be other wrestlers. So we still have to say that
The whole sentence says that it's about the wrestler, or the wrestler, and then X is D. Doesn't that mean that Dwayne is the wrestler?
you can say Dwayne is the wrestler, and then you need to have to include the information that no one else is the wrestler. So you can say, you're right, you can say for all Y, if Y is the wrestler, then Y is B. This will be an equivalent way of saying it, but this is kind of easier because remember we're just building up things like from the at least to the exactly. We're kind of building up all the concepts. The wrestler lives in Miami. Here I'm basically saying the F is a G, right? Because living in Miami Miami is a name and X lives in Y, that's a relation. So again, I have here the definite description, and I'm saying the X here lives in Miami. Okay. I can even, okay, the wrestler, is this a definite description? Yeah. The premier sports entertainer, is this a definite description? Yeah. So I can equate or can identify two definite descriptions in first order logic. It's going to be a long thing, but I'm basically saying there's exactly one wrestle and there's exactly one sports entertainer, and they are the same. Okay, so it's going to be a long sentence, but it's possible. Okay, this says there is exactly one wrestler. This says there is exactly one sports entertainer, and this says it's the same individual, The Rock. Okay? From counting to definite descriptions. It's kind of like I'm giving you a very short history of logic in the 20th century here. Russell used the very fun sentence in his paper that got published. The present king of France is bald. He wanted to make fun of the French. They don't have a king. He's from England. He noticed you have the present king of France is bald. The present king of France, this is a definite description, and then you give it the property, it's bald. But you can also say the present king of France is not bald. Okay? There is something very weird happening here. There are no French monarchs, right? So this definite description does not apply to anyone. Is this sentence true? No, it's false, right? Because there are no French monarchs. But when we said if we have a false sentence and we negate it, we should get a true sentence, right? So here we negate it, but this is also false. Okay, we have a weird situation where we have a false sentence. We add a negation, it remains false. Okay? That's again a place where people said, logic cannot handle something, right? The negation is supposed to flip the truth values, but it doesn't work here in this English sentence. Okay? We call it the no gaps or group assumption. Right? Everything is either true or false, but not both, or not. What do? We okay, the negation can also be in a different place. How can you negate this sentence in a way that makes it true? Easier, yeah?
There's no present king of France that is bald.
All right, or you can just say it's not the case that the present king of France is bald. Right? So I need to put the negation outside. There's a difference. There's a difference between saying it's not true that the present king of France is bald versus the present king of France is not bald. The negation shows up in different places, and voila, the logic can show that exactly. So the present king of France is bald. The F is in G. So I start by saying there is a king. There is only one king. So any other French king is the same person, and that person is bald. The present king of France is not bald. Where would I put the negation? What do you say? No. He's not bald. Where is the bald claim showing up? At the end. So I can put a negation here. I put a negation here. There is still no X that satisfies this entire thing. Both of these sentences are going to be false. But I can, where would I put the negation if I want to say it's not the case that the present king of France is bald? Where would I put a negation? In front, right? So there's a difference here. This is saying it's not the case that the present king of France is bald, which is a true sentence.
The negation in the second sentence will never flip the whole truth value for the whole sentence.
Right. Yeah.
So only in the third sentence that happens, so that's still true. The negation flips the whole truth.
Yes, exactly. So you have to be very careful about the way you position the negation, and first order logic can show you exactly where to put the negation in order to always flip the true value of the sentence. Yes. Yeah, you want to make sure that you're negating the entire conjunction.
I know, but like this one sentence, you just negate it out there.
So it has a structure, and it's basically,
Oh, yeah.
right, so you want to make sure that you negate both, yeah, and good. Yeah.
Why do you have to specify the second thing, like if there's any king of France, then that is the same king?
Because I want to make sure that it's a definite description, it only applies to one thing. Remember, the teacher is not a definite description, there are many, many teachers around us. So I want to somehow rule out the multiplicity.
Okay, so if there's the before something in a sentence, we just have to do it everything.
As a definite description. Think about it, when you use the in English, then you mean the one particular thing. This is why you have a distinction between when you learn there's like B something and A something, or M, right? This talks about indefinite, and this is like definite. One thing, and this is like maybe many things. Okay, how are we with time? We are out of time. We will cover what is the exact definition of a sentence next time. We can wait with that. Don't worry about it. This is the important stuff, identity and definite descriptions, okay, for the homework.